Welcome to a profound journey into the heart of reality, presented to you exclusively by the team at Astrum Discovery Network. We begin our story in the quiet desert of New Mexico, where humanity first unlocked the terrifying power hidden inside matter. It was here that the theoretical physics of the early 20th century was about to become a violent and undeniable reality. Scientists gathered to witness the moment when the smallest building block of the universe would unleash the greatest energy ever seen. In a fraction of a second, the desert sand turned to glass, proving that the atom was not just a solid sphere. This event marked a turning point in history, showing us that matter contains vast amounts of energy waiting to be released. But to understand how we got here, we must travel back thousands of years, long before we could split the atom. The question of what the world is made of has haunted philosophers and scientists since the very beginning of human civilization. If you take a piece of matter and cut it in half, and then cut it again, where does it end? An ancient Greek philosopher named Democritus was the first to propose that there must be a limit to this division. He called these fundamental particles atomos, meaning uncuttable, believing they were the smallest solid building blocks of everything we see. For centuries, this idea remained a philosophical concept, buried in scrolls and debated by scholars without any physical proof to support it. It was not until the 19th century that scientists began to find experimental evidence that these tiny particles actually existed in reality. John Dalton formulated the first modern atomic theory, suggesting that elements are made of atoms with specific weights and distinct properties. This organized the chaotic world of chemistry into a structured system. But the atom was still thought to be a solid ball. Then came J.J. Thomson, who shattered the idea of the solid atom by discovering something smaller inside it, the electron. He proposed the plum pudding model, imagining the atom as a positive sphere with negative electrons scattered throughout its internal structure. But his student, Ernest Rutherford, would soon prove him wrong, with one of the most famous experiments in the history of physics. Rutherford fired alpha particles at a thin sheet of gold, expecting them to pass right through the soft plum pudding atom. To his shock, some particles bounced back, as if they had hit something incredibly small, dense, and heavy in the center. He had discovered the nucleus. The atom was mostly empty space, with almost all its mass concentrated in a tiny central point. If an atom were the size of a football stadium, the nucleus would be just a marble sitting on the center line. Later, James Chadwick discovered the neutron, a neutral particle sharing the nucleus with the proton, completing our picture of the atom. For a while, humanity thought we had solved the puzzle. Protons, neutrons, and electrons seemed to be the fundamental building blocks. But the story was far from over. Lise Meitner, a brilliant physicist, would soon discover that the nucleus itself could be split. She realized that if you hit a large nucleus hard enough, it splits, releasing the massive energy that binds it together. This discovery of nuclear fission led directly to the bomb, proving that matter is just a condensed form of immense energy. After the war, physicists built powerful machines to smash atoms together, hoping to see what else lay hidden inside the nucleus. They expected simplicity, but instead they found chaos. Hundreds of new, strange particles appeared in their detectors, confusing everyone involved. They called it the particle zoo. It seemed impossible that the universe was made of so many different fundamental ingredients. Murray Gell-Mann stepped forward to bring order to this chaos. He proposed that protons and neutrons were not fundamental after all. He theorized that they were made of even smaller particles, called quarks, with strange names like up, down, and strange. This theory simplified the particle zoo. Everything could be explained by combining these few quarks in different ways and patterns. This became the standard model of particle physics, the most successful theory ever created to describe the building blocks of matter. But there was a huge problem. The mathematical equations suggested that all these particles should have no mass, flying at light speed. Peter Higgs and others proposed the solution: an invisible field permeating the entire universe that gives particles their mass. Imagine a cosmic ocean. Some particles swim through it easily, while others get bogged down, gaining mass as they struggle through. Think of a famous person entering a party. People crowd around them, making it hard to move. This resistance is mass. An unknown person can walk through the crowd easily. They interact less with the field, so they have very little mass. The photon interacts with no one. It moves freely at the speed of light, having absolutely no mass whatsoever. To prove this field existed, scientists needed to find its associated particle, the Higgs boson. The race was on to find it. Fermilab, in the United States, built the tevatron, smashing protons and antiprotons together for decades, hunting for the elusive God particle. They narrowed down the search, getting closer and closer, but the tevatron eventually ran out of energy and time. The torch was passed to Europe. CERN built the Large Hadron Collider, the biggest and most complex machine in human history. Deep underground, they accelerated protons to 99.99% the speed of light, recreating conditions just moments after the Big Bang. Trillions of collisions happened every second. Supercomputers filtered the data, looking for a tiny signal hidden in the massive background noise. On July 4th, 2012, the world held its breath. The data showed a clear bump. We had finally found the Higgs boson. It was a triumph for human intellect. A prediction made 50 years earlier using only mathematics was proven true by reality. The standard model was complete. We knew the ingredients of the universe. But this answer led to an even deeper mystery. Quantum field theory tells us that particles are not actually solid objects at all. They are just excitations in invisible fields. Imagine the universe is filled with fluid fields. A particle is just a ripple in that fluid, a localized vibration. There is an electron field everywhere. An electron is just a knot of energy where that field is vibrating intensely. The universe is not made of things, it is made of fields. The solid world we touch is an elaborate illusion. When you touch a table, you are not touching matter. You are feeling the repulsion between the electromagnetic fields of your atoms. Interestingly, this modern scientific view mirrors ancient Indian philosophy, which described the world as Maya, or illusion, created by energy. Thousands of years ago, they sensed that the solid world was a manifestation of underlying vibrations, a concept physics has now confirmed. So, what is everything made of? It is made of energy, vibration, and fields, dancing in the empty void of space. The journey is not over. Dark matter and dark energy remain unexplained, waiting for the next generation of curious minds to discover. From the desert of New Mexico to the tunnels of Geneva, we have peeled back the layers of reality, one by one. Thank you for joining us on this incredible exploration of the subatomic world. This has been a production of Astrum Discovery Network. Let us look closer at the pioneers. Marie Curie's work on radioactivity was the first clue that atoms were not immutable. She found that certain elements spontaneously released energy, suggesting that the atom was unstable and undergoing some kind of internal change. Henri Becquerel accidentally discovered that uranium salts could expose photographic plates, proving that energy was coming from within the stone itself. Scientists soon identified 3 types of radiation: alpha, beta, and gamma, each revealing different secrets about the structure of the atom. Niels Bohr took these ideas and applied quantum theory, suggesting electrons move in fixed orbits, like planets around a miniature sun. This model explained why atoms emit specific colors of light. The quantum leap was born, describing the sudden jump of electrons. Werner Heisenberg then introduced the uncertainty principle. We cannot know both the position and speed of a particle at once. The neat planetary orbits were replaced by probability clouds. The electron was no longer a point, but a smear of potential. Erwin Schrödinger formulated the wave equation, describing how these quantum states evolve over time, further blurring the line between wave and particle. Paul Dirac combined quantum mechanics with special relativity, predicting the existence of antimatter, doubling the number of known particles instantly. Carl Anderson soon found the positron, the electron's antimatter twin, confirming that for every particle there is a mirror opposite. When matter and antimatter meet, they annihilate each other, turning their mass completely back into energy, following Einstein's famous equation. Einstein's E equals mc squared told us that mass is just concentrated energy. Breaking the atom releases this stored potential. Enrico Fermi built the first nuclear reactor in Chicago, proving we could control this fission chain reaction for energy production. This knowledge was quickly weaponized. The Manhattan Project gathered the world's brightest minds to build the gadget that would end the war. Among them was Richard Feynman, a young genius who would later revolutionize our understanding of how particles interact with each other. He invented Feynman diagrams, a visual language that turned difficult calculations into simple drawings of particles exchanging force carriers. For example, the electromagnetic force is just the exchange of virtual photons between charged particles, like players tossing a ball. Physicists identified 4 fundamental forces governing the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force.
The strong force is what holds the nucleus together, overcoming the repulsion between protons. It is the strongest force in nature. The weak force is responsible for radioactive decay. It allows particles to change their identity, turning neutrons into protons. Wolfgang Pauli predicted the neutrino to solve a missing energy mystery. He called it a desperate remedy to save physics. Neutrinos are incredibly elusive. Trillions of them pass through your body every second, coming from the sun, without you feeling anything. To catch them, we built massive underground tanks of pure water, lined with sensors, waiting for a rare collision to occur. When a neutrino hits a water molecule, it creates a faint flash of blue light, proving the existence of these ghost particles. Scientists Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that at high energies, the electromagnetic and weak forces merge into one. This electroweak theory was a major step forward, unifying 2 of the 4 forces and earning them the Nobel Prize. Back in California, the SLAC linear accelerator was firing electrons at protons like bullets to probe their internal structure deeply. The scattering patterns confirmed Gell-Mann's theory. The proton was not solid. It had 3 distinct points of charge inside it. This led to quantum chromodynamics, or QCD. It describes how quarks interact via the strong force, similar to electric charge, but stronger. The force carrier is called the gluon because it literally glues the quarks together to form protons and neutrons. Quarks are never found alone. If you try to pull them apart, the energy creates new quarks. This is called confinement. We discovered that matter comes in 3 generations. The first makes up our world. The other 2 are heavier, unstable copies. The electron has heavy cousins, called a muon and a tau. They behave exactly the same, but decay quickly into lighter particles. Why are there 3 generations? Why not 1 or 4? This remains a mystery that the standard model does not answer. In the very early universe, it was too hot for protons to form. The cosmos was a quark-gluon plasma soup. As the universe cooled, these quarks got trapped together forever, forming the hydrogen and helium nuclei that make up stars today. Neutron stars are the only places in the modern universe where matter is compressed back to nuclear density on the macroscopic scale. At CERN, keeping the LHC running requires cooling the magnets to temperatures colder than deep space using liquid helium. This extreme cold allows electricity to flow without resistance, creating the powerful magnetic fields needed to steer the proton beams. The LHC produces so much data that it cannot all be saved. Intelligent algorithms must decide instantly what to keep. This data is distributed to computing centers around the world, creating a global network of analysis to find new physics. Physics loves symmetry. The standard model is built on mathematical symmetries that dictate how particles and forces must behave. But for the universe to be interesting, symmetry must be broken. The Higgs field breaks the symmetry, allowing particles to have mass. Without the Higgs boson, electrons would have no mass. They would not orbit nuclei, and atoms, stars, and life could not exist. Mass is what gives the universe structure. It allows gravity to pull matter together to form galaxies, suns, and planets. The top quark is the heaviest known particle, as heavy as a gold atom, yet it is a single point. Why the top quark is so heavy and the electrons so light is a question the standard model cannot answer. We also know the standard model is incomplete because it does not account for dark matter, which makes up most of the universe. We are hunting for dark matter particles deep underground, but so far they have evaded detection, remaining a cosmic mystery.
Then there is dark energy, an unknown force accelerating the expansion of the universe, pushing galaxies apart faster every day. Everything we have studied, atoms, quarks, stars, makes up only 5% of the universe. The rest is unknown. Some theorists propose string theory, suggesting particles are not points, but tiny vibrating strings existing in higher dimensions. These extra dimensions might be curled up so small that we cannot see them, but they determine the properties of particles. However, string theory has yet to be proven by experiment. It remains a beautiful mathematical framework waiting for physical evidence. Another idea is supersymmetry, predicting that every particle has a heavy partner. The LHC has been searching for them. So far, the LHC has found no signs of supersymmetry. Nature seems to be more complex or different than we expected. Physicists are guided by beauty and elegance in equations, but the universe is under no obligation to be simple or elegant. Despite the mysteries, quantum field theory remains our best map of reality. It explains almost every experiment we have ever done. Even empty space is not empty. It is a seething foam of virtual particles, appearing and disappearing in nanoseconds. We can measure this activity. The Casimir effect proves that the vacuum of space is full of quantum energy and pressure. Some scientists worry our vacuum might not be stable. A quantum fluctuation could theoretically rewrite the laws of physics instantly. To probe deeper, we are planning even bigger machines. The future circular collider would be 100 kilometers in circumference. China is also planning a massive collider. The quest to understand the fundamental nature of matter is a global human endeavor. This isn't just abstract theory. Antimatter is used every day in hospitals for PET scans to detect cancer and save lives. The World Wide Web was invented at CERN to help physicists share data. Fundamental research often leads to unexpected technological revolutions. Your smartphone would not exist without our understanding of the electron and quantum mechanics. Physics powers the modern world. We have come a long way from the simple hydrogen atom. We have deconstructed reality down to its vibrating foundations. Every atom in your body was forged in the heart of a dying star. We are literally stardust, contemplating itself. As Carl Sagan said, we are a way for the universe to know itself. Our curiosity drives us to explore the unknown. The search for the smallest particle brings us back to the largest questions about the origin and fate of the universe. The physics of the very small determined the structure of the very large. The Big Bang was a quantum event. Stephen Hawking showed us that black holes connect quantum mechanics and gravity, a clue towards a theory of everything. The theory of everything remains the Holy Grail, a single equation that would explain all matter and forces in the cosmos. Perhaps one of you watching this video will be the one to crack the code and complete the picture of reality. As we master the quantum world, we are building quantum computers that will solve problems impossible for classical machines. Quantum entanglement shows that space is not what we think. Particles can remain connected across vast distances instantaneously. John Bell proved that this weirdness is real. The universe is fundamentally probabilistic, not deterministic like a clockwork machine. Einstein refused to believe God plays dice with the universe, but the evidence suggests that chance is built into reality. The act of observation affects reality. The wave function collapses into a particle only when we measure or interact with it. Some interpretations suggest a multiverse. Every quantum decision splits the universe into branching realities, creating infinite parallel worlds. In this vast, complex multiverse, are we the only ones asking these questions? Or is consciousness a fundamental part of matter? Roger Penrose suggests that consciousness itself might be a quantum phenomenon, linking the physics of the atom to the human mind. Carbon, nitrogen, oxygen, these simple atomic structures, arranged in complex patterns, give rise to the miracle of life and thought. We have filled the periodic table. We have mapped the standard model, but the map is not the territory. What are these fields made of? Are they physical, or are they purely mathematical structures that describe our observations? Max Tegmark
proposes that the universe is not just described by math, but is mathematics itself. Reality is a mathematical structure.
Science teaches us humility. Every answer opens 10 new questions. The horizon of knowledge keeps moving further away as we advance. From the quark to the proton, the atom to the molecule, the sand grain to the planet, it is all connected. Light itself, the photon, is the messenger. It carries information across the universe, allowing us to see back in time. With telescopes like James Webb, we look back to the beginning, seeing the first atoms forming in the early universe. Inside stars, simple protons are crushed together to form heavier nuclei. This alchemy created the elements of the Earth. When massive stars die, they explode. The intense heat of a supernova forges the heavy elements like gold and uranium. This enriched dust condensed to form our solar system. The atoms in your hand were once inside an exploding star. Matter is recycled. It is neither created nor destroyed, only transformed from one state to another in a cosmic cycle.
Will matter last forever? Some theories suggest protons might eventually decay, causing all matter to dissolve into radiation. We have watched for proton decay, but haven't seen it yet. If it happens, it would mean the end of matter. In the far future, the universe may become a cold, dark void, populated only by radiation and evaporating black holes. But for now, we live in the Goldilocks era. The universe is rich with structure, energy, and the complexity of life. Carbon atoms bond in infinite ways, creating the complex molecules of DNA that carry the instructions for life itself. Water, a simple molecule of hydrogen and oxygen, has unique properties that allow life to thrive on our blue planet. Electrostatic forces hold atoms together in crystals and molecules. It is the glue that builds the macroscopic world we see. Beyond solid, liquid, and gas, there is plasma. Ionized gas makes up 99% of the visible universe, including all stars. At extreme cold, we create Bose-Einstein condensates, where atoms lose their identity and merge into a single quantum wave. Superfluids flow without friction, climbing walls and defying gravity, showing quantum mechanics operating on a scale we can see. Superconductors carry electricity with zero loss. They are the key to powerful magnets and efficient energy grids of the future. We are designing new forms of matter, like graphene, a single layer of carbon atoms with miraculous strength and conductivity. Nanotechnology allows us to manipulate matter, atom by atom, building materials and machines with precision previously thought impossible. The alchemists dreamed of transmuting lead into gold. Today, we can actually do this in particle accelerators, though it's expensive. We have gone beyond nature, creating synthetic elements that exist only for a fraction of a second in our labs. Physicists hope to reach the island of stability, where super heavy elements might exist long enough to be useful materials. Yuri Aganesyan is the only living person with an element named after him. Element 118 marks the current edge of matter. Is there a limit? At some point, the nucleus becomes too large to hold electrons, and the atom falls apart instantly. Antimatter is not just sci-fi. A banana releases a positron every hour or so due to natural radioactive potassium decay. The biggest mystery is why we exist. The Big Bang should have created equal matter and antimatter, annihilating everything instantly. We discovered CP violation, a slight asymmetry that allowed a tiny fraction of matter to survive and build the universe. We are the leftovers. 1 out of a billion particles survived the Great Annihilation to form the galaxies, stars, and us. Mass connects the quantum world to gravity, but we still don't know how to fit gravity into the standard model. We hypothesize a particle called the graviton, but gravity is so weak that detecting a single graviton is currently impossible. Some feared the LHC would create micro black holes. Even if it did, they would evaporate instantly due to Hawking radiation. Nature bombards Earth with particles far more energetic than our machines. If the LHC were dangerous, the sky would have killed us. Cosmic rays are protons from supernovas and black holes, traveling across the universe to strike our atmosphere every second. In fact, the heavy electron, the muon, was first discovered not in a lab, but by studying these cosmic rays. At the South Pole, the Ice Cube Observatory uses a cubic kilometer of ice to catch neutrinos from the most violent cosmic events. We have entered the era of multi-messenger astronomy, using light, particles, and gravity waves to understand the universe's composition.
LIGO detected gravitational waves, ripples in the fabric of space-time itself, caused by the collision of massive black holes.
Inside the black hole, matter is crushed into a singularity. We do not yet have the physics to describe this state. Does information get destroyed in a black hole? This paradox is a major battleground between quantum mechanics and gravity. The holographic principle suggests that our three-dimensional reality might be a projection of information stored on a distant 2D surface. If the universe is pixelated at the smallest scale, could we be living in a simulation? It is a serious scientific question. The Planck length is the smallest possible measurement. Below this, the concepts of space and geometry cease to make sense. Similarly, time might not be a continuous flow, but a series of discrete ticks, like frames in a movie reel. Many physicists now believe space and time are not fundamental.
They emerge from the quantum entanglement of more basic components. We return to the idea that form is temporary. The underlying field, the quantum ocean, is the only permanent reality. The statue of Shiva at CERN symbolizes the cosmic dance of creation and destruction, a metaphor for the particle world. Like Indra's net in Buddhist philosophy, every part of the universe is connected to every other part through quantum fields. The Buddhist concept of emptiness is strikingly similar to the quantum vacuum. It is not nothing, it is the potential for everything. Science explores the outer world, spirituality explores the inner world. Both conclude that separation is an illusion of the senses. We are the universe's eyes and ears. Through our consciousness, the quantum fields have become aware of their own existence. With this knowledge comes power. We can destroy our world with nuclear fire or solve our greatest challenges with technology. Understanding the physics of a flower does not subtract from its beauty. It adds a deeper layer of wonder and awe. Richard Feynman famously argued that scientific knowledge only enhances the mystery and beauty of the universe, never diminishing it. In these 35 minutes, we have traveled from the dawn of the atomic age to the cutting edge of quantum theory. So, what is everything made of? Not hardballs, but vibrations. Not stuff, but stories written in the language of math. The old materialism is dead. The universe is more like a great thought than a great machine, dynamic and alive. This is just the beginning. We encourage you to dive deeper, read more, and keep asking the hard questions about reality. Join our community of explorers. Share your thoughts and theories in the comments below. We love reading your perspectives. Subscribe to Astrum Discovery Network for more deep dives into the cosmos, technology, and the history of scientific discovery. A special thank you to our supporters who make these high-quality productions possible. You are the fuel for our journey. The universe is vast, and our time is short. But in that short time, we can understand the infinite. Let us take a moment to appreciate the sheer improbability of our existence and the stability of the matter that makes us. The proton has been stable for 13 billion years. It is the bedrock upon which the cathedral of the universe is built. The electron, dense and on the outside, gives the world its flavor, its color, and its texture. It is the artist of nature. The neutron, the silent partner, keeps the peace in the nucleus, allowing complex elements to exist without blowing themselves apart. And the photon, the storyteller, travels across the void to bring us the news of what happened eons ago. Up quark, down quark, electron, and neutrino. These four particles form the first generation, the building blocks of our daily life. It is humbling to realize that the complexity of a city, a forest, or a human brain arises from just these four. Mathematics is the loom upon which these particles are woven into the fabric of reality. It is the universal language. As Galileo said, the book of nature is written in the language of mathematics. Without it, we are wandering in a dark labyrinth.
Physics underlies chemistry. Chemistry underlies biology. To understand life, we must ultimately understand the atoms that dance within us. The future of discovery is bright. New tools, new minds, and new questions will continue to push the boundaries of knowledge. Stay curious. Never stop asking why. The world is full of wonders, waiting for those with the patience to look closely. Look again at that dot. That's here. That's home. That's us. A collection of atoms thinking about itself. You are a universe of atoms, an atomic cathedral, a galaxy of particles. You are not separate from nature.
You are part of nature, a transient arrangement of stardust that has come together for a brief moment to experience consciousness. As we conclude this journey, carry this perspective with you. Look at the world not as things, but as vibrant energy. See the miracle in a drop of water, the history in a stone, and the mystery in the light of the stars. Fire is the sun's energy stored in wood, released back into the wild. It is a conversation between atoms. The wind is the collective movement of billions of invisible molecules, a ghostly force that shapes the landscape of our world. Lightning is the sky's way of balancing its charge, a massive electrical discharge that reminds us of nature's raw power. The tides are the moon reaching out with gravity to pull the oceans, a silent dance between celestial bodies. Snowflakes form because the water molecule is bent at a specific angle, forcing ice into beautiful six-sided symmetry. Earth, air, fire, and water.
The ancients saw the complexity, but they missed the underlying simplicity of the atoms. It has been an honor to guide you through the fundamental building blocks of our reality. Thank you for your time. This video was researched, written, and produced by the dedicated team at Astrum Discovery Network, committed to science education. Music and sound design were carefully selected to enhance your experience of this epic journey through space and time. If you enjoyed this, please watch our video on the Big Bang, or our deep dive into the mysteries of quantum mechanics. Don't forget to hit the subscribe button and the bell icon, so you never miss an update from our channel. Astrum Discovery Network is dedicated to bringing the universe down to Earth, making the complex simple and the invisible visible. As Einstein said, the most incomprehensible thing about the world is that it is comprehensible.